we often use in sciences, as well as in our everyday life, the word function, which is the most important concept of higher mathematics. For all of us, this word expresses some dependence of a quantity on another quantity, but a good answer to the question, what is a function, is not easy. At a not very rigorous mathematical level, we can say that a function is a relation or a rule, which connects two quantities x and y, so that, if x takes a value, then the rule gives one or more values to y. We express this relationship simply by writing, which we read as y equal to f of x. Thus, f and the parentheses represent the rule which relates the values of x and y. A similar definition of function uses the concept of correspondence or mapping of a value of x to one or more values of y, and can be described with the following figure. Let us see two examples of functions that we come across often in our daily life. Example 1. The payment a worker receives depends on how many hours he is working. Thus we write payment equals F, hours of work. Example 2. The price of a car depends on the power of its engine. Thus we write price of car equals F, power of engine. The previous definition of function using the concept of rule or mapping may be slightly modified, if we assume that for every x we have only one y. In any case, this is a good description, but it is not a good definition. A good definition needs to have certain good characteristics itself. In general, for a definition to be good, it must have two characteristics. 1. For the definition of concept A, only other known concepts are allowed to be used. This means that other unknown concepts or the concept A itself cannot be used. 2. If we are given a concept or instance of a concept X, we must be able to answer the question whether X is or is not A. Unfortunately, the previous description of function is not a good definition, because to define the concept of function we use the concept rule, which is essentially the same concept. The same happens with the other definition of function, according to which, a function is a mapping of one set of values of x to another set of values of y, since the concept of mapping is used, which again is essentially the concept of function. These two descriptions can be used as definitions in technological or economic sciences, where mathematical rigorousness is not necessary. In rigorous mathematics, however, the description of a concept is not enough and a good definition is required. To give a good definition of function, we start from the basic concepts of set and element of set. These concepts are primitive. This means that we accept them as known, without defining them. The acceptance of certain concepts as known, even in science, is a fundamental human inadequacy, since we always need to rely on something in order to define or build something new. We denote a set with a bracket, which encloses either all the elements explicitly or a clear description giving all the elements. Thus, for example, the set A equal a bracket enclosing the numbers 1, 3, 5, 7, 9. Is the set of all odd numbers between 0 and 10. An element of A, like 3, is denoted by 3 element of A. Also we can write the same set in the form A equals a bracket, a symbol n, and a small vertical slash followed by a short description of n, as an odd integer between 0 and 10. According to this notation, We write inside the bracket a symbol representing the element and a small vertical slash followed by an expression giving clearly the various elements. The elements of a set may be anything, but we will restrict them to numbers for simplicity. For the concepts of set and element of set we have the following. 1. A set A is called subset of another set B, if every element of A is an element of B. This relation is denoted as follows. 2. Two sets A and B are equal, if and only if each of them contains exactly the same elements with the other. In this case, each set is a subset of the other and we write A equal B, or equivalently A is contained in B, and at the same time A contains B. 3. The order in which the elements of a set appear inside a bracket is not significant. This means that the elements of a set do not have any order attached. For example, the set 1, 2, is the same as the set 2, 1. Also, every element is written only once inside the bracket, since there is no reason or meaning to write it more times. Thus the set 1, 2, is the same as the set 1, 2, 2. 4. A set can have elements which are sets themselves. For example, the set C is a set with 3 elements, the numbers 1, 2 and the set with elements 3, 4. We define now the ordered pair as follows. Where A and B are elements of the same or different sets. This means that an ordered pair is a set with 2 elements. The first element is the set with a single element A and the second element is a set with 2 elements A and B. Let us note that an ordered pair is denoted with a parenthesis, while a set is denoted with a bracket. Example, let A be the set with elements 1, 2, 3 and B the set with elements K and L. Using an element of A and an element of B we can form several ordered pairs, as for example the ordered pair 1, K and many more. For ordered pairs, we can prove easily the following theorem. If two ordered pairs, A, B, and C, D, are equal, then A equals C and B equals D. Obviously, the reverse is also true. Note that this theorem allows us to talk about first and second element of an ordered pair, while we cannot talk about first and second element of a set. The first element of the ordered pair, A, B, is A, and the second element is B. We come now to the Cartesian product of two sets. The Cartesian product of two sets A and B is the set of ordered pairs A and B, where lowercase a is an element of A and lowercase b is an element of B. Example 1. Let A be a set with elements 1, 2, 3 and B a set with elements A and B. The Cartesian product A cross B is the set with the following ordered pairs. 1a, 1b, 2a, 2b, 3a, 3b. Example 2. The Cartesian product Z cross R of the sets Z and R, where Z is the set of integers and R the set of the real numbers, is the set of the pairs, NR, where N is an integer and R is a real number. Note that we cannot write all the elements of Z cross R, because they are infinite. We define now at last the concept of function with a good definition. A function f from a set D to a set R is a set f of ordered pairs, x, y, which is a subset of the Cartesian product D cross R, such that for every x element of D there is a unique y element of R with the pair x, y element of f. With symbols, we write a function as follows. In this form, D is the set of the values of x and is called domain of definition of the function, and R is the set of values of y and is called range of the function. Often, we do not give precisely R, or we give a larger set, since its elements are given from f of x for every x element of D. Thus, a function is determined completely from the domain of definition D, and f of x, which gives the corresponding y. We call x the independent variable and y the dependent variable. We can also delete the domain of definition D, and give for a function only f of x. In such a case, it is assumed as domain of definition the largest possible D, for which f of x has meaning. Consequently, we obtain again the simple definition of function from f of x only, keeping in mind that behind this abbreviation there is a rigorous definition, which was presented above and to which we can refer whenever we need to do so. Now that we know the concept of function, let us give some examples of functions. Example 1. The function f1 from a to b, where a is the set with elements 0, 1, 2, 3, and b is the set with elements 0, 1, 4, 9. The function f1 is defined as the set with elements the ordered pairs 0, 0, 1, 1, 2, 4, 3, 9, is a subset of A cross B, and for each x element of A there is a unique y element of A such that the pair, xy, is an element of the set f1. Example 2. The function f2 from D to R, where D is the set of real numbers between -1 and 2, and R is the set of the real numbers. The dependent variable y does not get all the values of R, but it is restricted to the values given by the relation f2 of x equal to x squared plus 2, which means that the range is contained in R. Note that for x equal to -0.5 and x equals 0.5 we obtain the same y equal to 2.25, but this does not violate the definition. Finally, let us give an example that is not a function. Example 3. If D is the set with elements -1, 1, 2, 3, R is the set with elements 1, 4, 9, and H is the set with elements the ordered pairs -1, 1, 1, 1, 1, 4, 2, 4, 3, 9, then H is not a function, because for x equals 1, the set H contains the pairs 1, 1, and 1, 4, which means that for x equals 1 the value of y is not unique. At least one of these pairs must be changed to fulfill the requirements of the definition. If the relation between x and y is given in another way, for example with an equation y equals f of x for each x element of D, then for each x element of D this relation must give a unique value of y element of R. Conclusion. The whole procedure for the definition of function can be presented with a figure. We started from the concepts of set, and element of a set, we defined the ordered pair, then the Cartesian product, and finally the function. The final rigorous definition is given above. Simply, we can say the following: a quantity y is a function of another quantity x, if there is a rule, which for one value of x gives one value of y. Anyone using the concept of function can choose to use whatever definition he wants, depending on the particular area of science he works. In any case, however, it is very useful to know exactly what y as a function of x means.